This episode is brought to you by Cisco Educational Premium. Did you know that Planck units are units of measure? In particle physics and physical cosmology, Planck units are a set of units of measurement defined exclusively in terms of four universal physical constants, in such a manner that these physical constants take on the numerical value of 1 when expressed in terms of these units. Originally proposed in 1809 by German physicist Max Planck. These units are a system of natural units because their definition is based on properties of nature, more specifically the properties of free space, rather than a choice of prototype object. They are relevant in research on unified theories such as quantum gravity. The term Planck scale refers to quantities of space-time energy and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 raised to 19 gigavolts or 10 raised to 9 joules. Time intervals of around 10 raised to negative 43 seconds and lengths of around 10 raised to negative 35 meters, approximately the energy equivalent of the Planck mass, the Planck time, and the Planck length respectively. At the Planck scale, the predictions of the standard model, quantum field theory, and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. The best known example is represented by the condition in the first 10 raised to negative 43 seconds of our universe after the Big Bang, approximately 13.8 billion years ago. The four universal constants that by definition have a numerical value of 1 when expressed in these units are 1. The speed of light in a vacuum c. 2. The gravitational constant g. 3. The reduced Planck constant h. And 4. The Boltzmann constant k sub b. Planck units do not incorporate an electromagnetic dimension. Some authors choose to extend the system to electromagnetism by, for example, adding either the Coulomb constant k sub b is equivalent to 1 on 4 pi E naught or electric constant E naught to this list. Similarly, authors choose to use variants of the system that give other numerical values to one or more of the four constants we have seen. Any system of measurement may be assigned a mutually independent set of base quantities and associated base units, from which all other quantities and units may be derived. In the International System of Units, for example, the SI base quantities include length with associated unit of the meter. In the system of Planck units, a similar set of base quantities and associated units may be selected, in terms of which other quantities and coherent units may be expressed. The Planck unit of length has become known as the Planck length, and the Planck unit of time is known as Planck time, but this nomenclature has not been established as extending to all quantities. All Planck units are derived from the dimensional universal physical constant that define the system, and in a convention in which these units are omitted, that is treated as having dimensionless value 1. These constants are then eliminated from equations of physics in which they appear. For example, Newton's law of universal gravitation. Of course, these Planck constants appear, so they are eliminated as shown by the second equation. Both equations are dimensionally consistent and equally valid in any system of quantities, but the second equation with g absent is relating only dimensionless quantities, since any ratio of two like dimensioned quantities is a dimensionless quantity. If By shorthand convention, it is understood that each physical quantity is the corresponding ratio with a coherent Planck unit, or an quote expressed in Planck units. The ratios we have seen may be expressed simply with the symbols of physical quantity without being scaled explicitly by their corresponding unit. This last equation without G is valid with F prime, M1 prime, M2 prime, and R prime, being the dimensionless ratio quantities corresponding to the standard quantities written, for example, F prime being F or F prime being F1, F3, but not as a direct equality of quantities. This may seem to be what setting the constant Cg etc. to 1 if the correspondence of the quantities is thought of as equality. For this reason, Planck or other natural units should be employed with care, referring G is equivalent to C is equivalent to 1. Paul S. Wilson wrote that mathematically it is an acceptable trick which saves labor. Physically, it represents a loss of information and can lead to confusion. The concept of natural units was introduced in 1874 when George Johnston Stoney noted that electric charge is quantized. Derived units of length, time, and mass now named Stoney units in his honor. Stoney chose these units so that G, C, and the electron charge E would be numerically equal to 1. In 1899, 1 year before the advent of quantum theory, Max Planck introduced what became later known as Planck constant. At the end of the paper, he proposed the base units that were later named in his honor. The Planck units are based on the quantum of action, now usually known as the Planck constant, which appear in the Wien approximation for black body radiation. Planck underlined the universality of the new unit system, writing, "It is possible to set up units for length, mass, time, and temperature, which are independent of special bodies or substances, necessarily retaining their meaning for all times and for all civilizations, including extraterrestrial and non-human ones, which can be called natural units of measure." Planck considered only the units based on the universal constants GH, C, and KB to arrive at natural units for length, time, mass, and temperature. These definitions differ from the modern ones by a factor of √2 pi, because the modern definitions use reduced Planck's constant rather than Planck constant. Unlike the case with the international system of units, there is no official entity that establishes a definition of a Planck unit system. Some authors define the base Planck units to be those of mass, length, and time, regarding an additional unit for temperature to be redundant. Other tabulations add, in addition to a unit of temperature, a unit for electric charge, so that either the Coulomb constant Ke or the vacuum permittivity E0 is normalized to 1. Thus, depending on the author's choice, this charge unit is given. Some of these tabulations also replace mass with energy when doing so. The Planck charge, as well as other electromagnetic units that can be defined like resistance and magnetic flux, are more difficult to interpret than Planck's original units and are used less frequently. In SI units, the values of CH, E, and KB are exact, and the values of E0 and G in SI units respectively have relative uncertainties of 1.5 times 10 raised to negative 10 and 2.2 times 10 raised to negative 5. Hence, the uncertainties in the SI values of the Planck units derive almost entirely from uncertainty in the SI value of G. Compared to the Stoney units, the Planck base units are all 1 on root alpha, approximately 11.7 times larger. In any system of measurement, Units for many physical quantities can be derived from base units. The table has a sample of derived Planck units, some of which are seldom used. As with the base units, their use is mostly confined to theoretical physics because most of them are too large or too small for empirical or practical use, and there are large uncertainties in their values. This episode is brought to you by Cisco Educational Premium.
The atom is the basic building block of matter around us. Your body, your clothing, your chair, your bed, even the device you're watching this video on is made of atoms. The idea of the atom is basically the reason why chemistry exists. The periodic table of elements is basically built on atoms. Ever since the idea of the existence of atoms was put forward by the philosopher Democritus, who said that the universe is made of atoms and the void in which they exist. This idea was since given a solid grounding by scientists, particularly chemists and physicists, proving its existence by scientific method. Today, there is solid evidence that atoms exist, and when we say that atoms exist, we really do know what we are talking about. An atom is most efficient as a dense and compact nucleus encircled by rapidly moving orbiting electrons. This concept naturally raises the question: how do electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass surrounded by tiny negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the sun orbited by smaller particles, the planets. However, this model posed two significant issues. First, charged particles that accelerate must emit electromagnetic radiation by observations and at least by Maxwell's equations. Since electrons are charged and accelerate during their orbits, they should emit radiation which will cause them to lose energy and quickly spiral inward into the nucleus. However, atoms are known to exist for much longer than a picosecond, making this model incorrect. Secondly, atoms were observed to emit radiation at specific frequency, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom do not just occupy any orbit but confined to specific distances from the nucleus. He also proposed that there was a minimum distance an electron could reach beyond which it could not move any closer to the nucleus. Those ideas were not just mere speculations. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus. He asserted that the smallest possible orbit of an electron will have an angular momentum equivalent to 1 Planck constant. High orbits would have integer multiples of the Planck's constant, such as twice or 3 times its value, but never fractions like half or 2 and 3. The full comprehensions of why electrons possessed specific orbits and well-defined energy levels required the more complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can usually visualize it as a wave enveloping a nucleus. Waves confined within a limited space must adhere to specific rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This is analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave circling a nucleus must fit the available space, and the nearest orbit is determined by fast standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying smaller space. However, an entirely different approach to understand this situation does not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around the nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, it possesses kinetic energy trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its potential and kinetic energies, is negative. Consequently, adding energy to the atom is necessary to remove an electron. This concept parallels the behavior of planets orbiting the Sun. To remove the planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling inwards towards the nucleus due to the attractive electric charge. However, because of the principle of quantum mechanics, the electron can never reach the nucleus, becoming perpetually in a stable orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding components together to form a long-lasting atom. Everything around us is composed of atoms. All the matter in the observable universe is estimated to be more than 10 quadrillion quintillion. This number is 1 followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. There are more technical details than this, which we are going to look at them. To understand the scientific perspective of the Big Bang, we need to examine the events of the early universe. Unfortunately, we do not have a definitive understanding of precisely when the universe started, or if it indeed started at all. Our base model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t is equal to 1. This theory predicts a singularity a moment of infinite density where all matter and energy were compressed into an infinitely small point. Most physicists predict that this prediction may not be entirely accurate. We can only go back to one Planck time, which is about 10 raised to negative 43 seconds. Before this, we have no knowledge of what occurred both by observation and mathematics. So while we get very close to the beginning, it is not precisely at t=1. Understanding the events of this incredibly small time scale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.